Determine whether the series from n equals 1 up to infinity of n times sine of 2 over n plus 1, all raised to the power n, determine whether this converges or diverges. Okay, so convergence, divergence, we start running through the list in our head. What convergence tests do we know? Which ones might apply here? And definitely for me, I would say the power of n here really screams to me root test. Because what do? First thing with a root test is, when it comes time to try and apply, should this test work, or should I do this convergence test, or that, it's good to sort of be able to mentally say, well, what would the first couple steps look like? Would that be simple? Do I think I'll make progress? And with the root test, the first thing you do is you nth root the expression, and that's going to cancel out this to the power n, just leaving us with n times sine 2 over n plus 1. So let's try and use the root test. It doesn't mean, by the way, that the root test will work. It's just that's a good instinct. You see that power of n there, and you know you can get rid of it. You know you can drop it. So let's apply, or maybe we should say let's try. Never assume that your first instinct is automatically correct, but let's apply the root test and see what happens. Okay. So for the root test, you use rho, the limit as n tends to infinity of the nth root of whatever sequence you're working with. And in this case, the limit as n tends to infinity of the nth root of n times sine 2 over n plus 1. Okay. Now this is positive. We don't need to throw any absolute values or anything like that. The root test just applies. You can see why that is. As n gets bigger, n is going to be positive. But 2 over n plus 1, that's going to approach 0 on the positive side. And if we quickly sketch sine, just because, just in case you want to be sure, are we applying the proper version of the root test to this? Sine looks like this, and as we approach 0, the 2 over n plus 1s that we're plugging in will be here, and this will be positive. Okay? So there's no oscillations, nothing weird, nothing hinky that makes us think, maybe I should use something like the alternating series test or something like that. No, it's straight, works just fine, and hey, we can cancel out the n and the nth root there. And what are we left with? Our rho should be the limit, as n tends to infinity, of n times sine 2 over n plus 1. And the question is, well, what is this limit? Well, as n gets really big, n tends to infinity, and as I was saying just a moment ago, the 2 over n plus 1, that goes to 0, and inside the sine, we'd say, that goes to sine of 0. Well, that's just 0. So what we have here is an infinity times 0 indeterminate form. Now, normally you can't do things with infinity, but symbolically infinity times 0 usually suggests, maybe we can simplify this. Maybe we can rewrite this in such a way as to get an answer. Okay? If we're clever, if we apply some techniques that we know, some helpful tricks, and one in particular, this is the one I think I'm going to use, is rewriting this to a 0 over 0 or infinity over infinity form, so I could try something like L'Hopital's rule. So we can bring the n to the bottom as a 1 over n, and then the bottom goes to 0, the top, as we've said before, goes to 0. So this is a 0 over 0 indeterminate form, and that's the sort that L'Hopital's rule applies to. Okay? So we can go ahead and try. So our rho here, I like putting the little L apostrophe H when I use L'Hopital's rule. It should be, assuming this limit exists, it should be the same as the limit of the derivative of the top over the derivative of the bottom. Okay. Now, depending on how comfortable you are with your derivatives, this might go slow, this might go fast. Okay. On the bottom, at least, 1 over n, that's going to go to minus 1 over n squared. On top, let's see, so chain rule, so derivative of sine cosine there, and then multiply by the derivative of 2 over n plus 1, so we can bring that 2 out, but what's the derivative of 1 over n plus 1? That'll be 1 minus, I don't want to think I'm subtracting, so we'll do minus 1 over n plus 1 squared, and then times the derivative of n plus 1, which is 1, so there we go. Okay. Now, before we go any further, we should try and simplify this a little bit. Anytime you use L'Hopital's rule, you should then try and cancel things out, rearrange, rewrite, and simplify. Otherwise, it is possible with L'Hopital's rule to get stuck in sort of loops. The minus signs will cancel. You can divide by 1 over n squared by multiplying by n squared up top. And then we got the cos of 2 over n plus 1. So now that we've got this, does this limit exist? Because if this is 3, then by L'Hopital's rule, the original limit, which is the row we're trying to calculate, would also be 3. For the record, I don't think the answer is 3, but it could be. Okay, so let's carefully analyze this. Do we have other indeterminate forms? Do we need to L'Hopital again? Do we need to try something else? So 2 over n plus 1, as n gets really big, this is going to go to 0. So this expression goes to cosine of 0, which is 1. And then we have something rational. We have a polynomial over a polynomial. This n plus 1 squared, we could expand it out as n squared plus 2n plus 1. And since the degree on top and the degree on bottom are the same, the limit of this portion here, this rational bit, is the ratio of the leading coefficients, 2 over 1. So this limit is going to be 2 over 1 times the limit of this cosine bit, which is 1. So we get 2. And I don't think we need a new page. We can just say, look, since we calculated this row, using L'Hopital's rule, and it's 2, and 2 is bigger than 1, by the root test, the series, the summation we're trying to do, I will say this series diverges. And there we go. That's our final answer. Or if we wanted to go back to the original, we could just say divergent. It diverges. That is the correct final answer here, thanks to the root test.